Okay, hi everyone. I have the pleasure of introducing our first seminar speaker of the academic year. I'm going to give a brief introduction to Dr. Noah Diffenbaugh, and then I'll let him take it away. Dr. Noah Diffenbaugh is a professor and senior fellow at the Dorr School of Sustainability at Stanford University. He received his bachelor's and his master's degrees in Earth Systems, both from Stanford, and his PhD in Earth Sciences from UC Santa Cruz. He studies the climate system, including the processes by which climate change could impact agriculture, water resources, and human health. So a great first seminar speaker for all the different areas that we research here in ESS. Dr. Diffenbaugh is also the inaugural editor-in-chief of a new peer-reviewed journal called Environmental Research Climate, and he was the editor-in-chief of Geophysical Research Letters, GRL, from 2014 to 2018. He has also served as a lead author for the IPCC, and he was elected Fellow of AGU and has been recognized as the Copley Fellow by the US National Academy of Sciences. So really lucky to have Dr. Diffenbaugh here, and please help me welcome him to ESS.
Thank you. And I should note it's a Copley Fellow. There's lots, including here in the room. So, okay, is it okay if I don't use my mask?
Yes, because we all have masks.
Okay, everyone's protected from me.
We protect you.
All right, let me. All right, here we go. It's great to be back here. I gave a talk, I think in 2009 or 2010 or so. And it's really exciting. You guys have such a great department. I frequently tell my research group that this is the best Earth System Science department. So it's exciting to be here. All right, I'm going to talk about work over the last decade or so, trying to quantify the causes and consequences of changes in extreme climate conditions over the historical period. Okay, excellent. So the alternative title is whatever terrible thing is happening right now where I am due to global warming, or even is the thing that's forecast to happen this weekend that's terrible due to global warming. So this is the question I and many others get from the public, and what we've been trying to figuring out whether we can do this in a hypothesis-driven way. I get an answer to this question by framing hypotheses, scientific hypotheses, and testing them. So you'll see different answers to this question. When I started my PhD, almost exactly 22 years ago, in the fall of 2000, if you ever saw a scientist answer this question, which you rarely did, you normally see them running away from this question back then. If they did answer, you get some reason of some version of, well, you know, we're talking about different things. You're talking about weather. We're talking about climate. That's totally changed, especially in the last decade. And now you'll see answers like this, which is an actual quote. I'm gonna move off it really quickly so you don't have time to Google it, but it's an actual quote. And this is true. Like, this is definitely not wrong. It's definitely between 0 and 100%. This is not wrong. But it would be great to narrow that, right? Not artificially, but to actually figure out where the answer is between 0 and 100%. This is a great room, by the way. I'm really comfortable in this room. Kind of want to stand over here, actually. Okay, I'm gonna try this. This is better. All right. Okay, so the way that we've approached this is essentially through a risk frame, right? It's the risk of, I mean, you can see this in the IPCC and elsewhere, right? The risk of some outcome from an extreme event is some function of the hazard, like the heat wave, the flood, the drought, etc. and the exposure and vulnerability. And most of what, if I can get the, most of what I'll focus on, at least in the first part of the talk, is on the hazard, and then I'm going to talk a bit more about how we, for quantifying impacts, and how we try to incorporate exposure and vulnerability into this as well. But the main point here is that our hope, and we'll see how you feel about it in 45 minutes. The hope is that this is scientifically tractable, right? That we're actually posing hypotheses and testing them. And it's it's practically actionable. There are real decisions that are being made that depend on the answer to this question. And this framing is a framing that is transferable to decision makers. It's not the core motivation for this analysis, but it is practically actionable potentially. Okay, so we've had a number of papers sort of wrestling with this question, and focus on this cartoon here to start to give you a sense of what sort of where we've landed, and this is both in my group as well as in general where the community is. And really the first paper trying to do this in a systematic way was back in 2004. The Stanford paper focused on the 2003 European heat wave, and now there's just hundreds and hundreds of papers doing this extreme event attribution, and they all basically do some version of what's on the screen now, right? So one thing I want to emphasize is that it's really important to define the event, right? When we say, is the event the heat wave, the flood, the storm surge from the hurricane, is that due to global warming? Is it being influenced by global warming? And really, the first step is really to define the event, and a lot of the debate that we've seen over the last decade or so about events, and even up to the present, has a lot of it has been that debates kind of going past each other because what the event is not defined, or not clearly defined. So we spend quite a bit of time trying to make sure we're defining the event before we move forward. And then, to answer this question, we have to have a counterfactual, right? And this is a real challenge for climate science, a real challenge for extreme event attribution, because we don't have, we can't run thousands of experiments on the whole world, right? We have one world, and to ask that question of what would have happened without global warming, if we don't have an experimental test bed for that, that's the global climate system. So there's a couple different approaches, and I'll show you some results using each of them. One is just to rely on the historical observations and basically use statistical approaches to remove the climate change, the detrend the data essentially, and just compare the observations, the real observations with the detrended observations to create counterfactual. There's lots of different methods for that, removing the climate change, but that's you don't have to use a climate model to do this. You can not believe in climate models, not want to use them, and still try to answer this question. The other approach is to use climate models, to use climate models as in the way that we would want to run experiments with, like I did in elementary school, where we grew corn seedlings in the window and in the closet and kept everything else the same. And then I really went for it in 8th grade and used the microwave, learned that cooking corn plant skills. But that's essentially what we want to do, right? We want to not saying the greenhouse effect is like, but we want to be able to run controlled experiments, and we can't find models with one way to do that. We can run lots and lots and lots of versions of history with different forcing factors, and then compare essentially the hypotheses from those climate models with what happened in reality. So the main point here is we need to compare what happened with counterfactual, and that's challenge. And then ultimately we want to make some formal attribution statement. And so you'll see in the literature or in the news, especially from the world weather attribution group that's doing this rapid attribution, you will see news headlines very soon after an event, and you're going to see these uncertainty statements that are applied that have a formal definitions that they've designed and published. And, okay, so that's the basic framework that we use, and most groups essentially use some version. So I'm gonna sort of go through the last 2 droughts here in California, more or less, that time period, not just talk about California drought, but I guess a third title of this talk could have been from counting and pattern correlation to causal inference and machine learning, something like that. So I'm going to sort of take you through and start out with kind of the simplistic ways that we started out doing this, and then take you up to what we're doing at the present. So my work on this, didn't actually start with the last California drought, but really kind of ramped up with the last California drought. And I'm not others here in the room work on this as well. Everyone here in California knows these have been really high impact events, but really with very severe conditions that are having severe impacts. And I want to note that in my experience, California has been very, very proactive in really engaging with scholars in real time, right? Scientists, engineers, and legal scholars to try to figure out how to address these conditions proactively. It's been a really, I think it's a great example of incorporating a cutting edge research into managing our evolving climates. Okay, so first, simplistic exercise. So, we had this paper back in 2015. There's the title, very definitive title, and is mostly a counting exercise. Right? So when we go back and look at the historical climate record from California, what we find down at that point, up until 2014, was that California's warming. Discovery. These are all downloaded data. Data downloaded from the website. So California's warming, right? Clearly. Not all warm years produce drought, but it's clear that the frequency of drought has increased in California, and in particular the frequency. In particular, the frequency that low precipitation years lead to drought has increased. So if we just take those data and just scatter plot them. So the horizontal is the precipitation anomaly, the vertical is the temperature anomaly, each dot is a year, and the brown and blue are the Palmer drought index. In this case, it's the massive PSI with the Palmer modified drought index. What we see is that if you look at the left, right, so this is over what at that point was the full California climate record. About a little more than half the years were drier than the long-term mean. But the key distinction here is the black, the 27%, the 26% versus the 54% and 25%. So what the orange numbers are showing is the percentage of low precipitation years that produce severe drought in California. And the point here is that not all low precipitation years produce drought. Not all warm years produce drought. But when a low precipitation year co-occurs with a warm year, it's twice as likely to produce severe drought in California. And if you look at the right, we're just pulling out the last 2 decades of the record at that point. The circle in both cases is 2014. And what you see is that because California has warmed, we're now just in a climate where it's much more likely that when low precipitation happens, it's also warm. And this is really, really simple. In the case of our analysis, we just count up years. And you can think of this that, it used to be California, temperature and precipitation were like flipping a coin, and you get heads, tails half the time on one coin, tails half the time on the other coin, you get 2 tails 25% of the time. If you're getting 80 or 90% warm years, you're just a lot more likely to get 2 tails. So super simple, just counting up years. We can then, that's just the historical observations. We can run or use, in this case, download the climate model experiments with and without human forcing. So what you see on the left is precipitation, and you can see both from the squiggles and from the p-values that there's really not much difference in mean annual precipitation, California statewide, with and without. That the California with human forcing is warmer than California without human forcing. So just as you would expect from the simple counting exercise, now if we repeat that with the climate model experiment, what we see is very high confidence that the increasing odds of the combination of low precipitation and high temperature, much higher odds of that with human forcing than without. So this is super duper simplistic. Peter Glick tweeted it early on in the drought. We bothered to do the counting and make the plots and submit it and got it. Okay, so that's the first order way in which global warming is influencing drought risk in California. And there are some other ways that also matter and that people also argue about. So one of them is this ridiculously resilient ridge. This was named by Daniel Swain, who at the time was a PhD student working with me. However, I did not know that he had named it that. So I was no, literally. So I was in my car waiting to pick up my daughter, sitting there in the car reading the news on the phone, and I think it was in The Economist. So I was, and this Economist article about the drought said the ridiculously resilient ridge. I was like, what the heck is that? Sounds ridiculous. Sorry, we're being recorded. Hey, Daniel. Yeah, so Daniel knows the story. So I was like, whoa, what is this thing? And I clicked on it and I find this blog. And it's the Weather West blog. Whoa, what's this blog? I've never heard of this. I click on the about, and there's Daniel, my PhD student. Anyway, so that's how I learned about Daniel's blog. Learned about Twitter later. Okay, so the point being here is that, as I'm sure you're all aware, right, the atmospheric pressure affects the atmospheric circulation and the progress of storms towards California. So in this early paper, and this is the point here is that the ingredients, the physical ingredients of extreme events matter, and it's important that we're analyzing that as well. So at the time that we published this paper, 2013 was the driest calendar year on record in California, and had the most extreme atmospheric pressure in terms of the 500 pascal heights in the reanalysis data set. And so we first proceeded to ask how rare this was and whether or not that probability was different with and without reinforcing. So turns out it's quite rare. The ridiculously resilient ridge was ridiculously rare, not these million-year return intervals, but definitely a rare event. And in this paper, we argued that based on simulations, that it was with high confidence, it was more probable, more likely with global warming and without. Then we want to get a little bit more. This has there's no spatial structure in this analysis, right? It's just over the Northeast Pacific probability of high pressure. So we went on to ask, and this is now, we've gone from counting to pattern correlation, so it's progress of my science. So the next question we asked was not just about the probability of high pressure over the North Pacific, but the probability of extreme gradients. And so when we look back historically, we find that in fact, as you see on the bottom right, that the years that have a ridiculously resilient ridge-like pattern show higher spatial correlation with what happened during the drought, have lower, overall have lower precipitation. So from a correlation point of view, exactly what we'd expect from our understanding of how the atmosphere works. So what we first asked was just about the, some people call the thermal dilation of the atmosphere. So just as the atmosphere has warmed, it had been argued that, well, this ridiculously resilient ridge can't be affected by global warming because the atmosphere is just warming uniformly, and we should see pressure, the atmospheric pressure increasing uniformly. In fact, we don't see that. Right? So on the top are the trends in the 500 millibar heights, and on the bottom when we calculate the thermal dilation from the atmospheric warming, and you can see that there's a lot of spatial structure to just the pattern of thermal dilation, and it is matches closely what we see in the trends of the 500 Pascal. So the observed trend is non-uniform, and much of it can be explained first order by just the simple thermal dilation downstairs. So we want to ask a little more quantitatively, since it's really these extreme gradients that are really responsible for these prolonged dry periods, has the probability of those extreme gradients changed? So we look at the recent period versus the early period, and what we see is that in fact the probability of extreme gradients upstream of California is much more likely now than earlier in the analysis. And in fact, that the difference is statistically significant. Also, if we just use simple pattern correlation to ask how often are years like the ridiculously resilient ridge, years like the recent drought, how often have they occurred through time, we find an increasing correlation overall. The atmosphere is becoming more like this pattern that promotes warm, dry, quote, wet seasons here in California. And there's a statistically significant difference in the recent period versus the earlier period. Okay, so that's sort of the first drought. This drought, the droughts had a lot of last drought, this drought had a lot of impacts, and many in the room, Jim and others have worked on impacts such as wildfire. So we've done a little bit on wildfire, asking again about what about these ingredients that tend to promote these hazards. So I'm going to show a few results from a paper that came out in 2020, led by Mike Goss. So when we look at, in this paper, we were particularly focused on autumn. And the reason we're focused on autumn is that in recent years, we've had these very extreme wildfires in the autumn season, including in multiple locations across the state. So in particular, in this case, the boxes show the Woolsey fire here in Southern California and the Paradise fire in Northern California. And this was an instance where there were not enough resources to respond to both fires simultaneously, and in particular having such extreme conditions so late in the year in both Northern and Southern California. So the maps are showing the trends in temperature, precipitation, and the fire weather index here in the autumn season. And what you can see is warming throughout California with spatial heterogeneity. Less statistical significance, but still clear trend statewide and through most of the state, decreasing precipitation trend, so getting drier in the autumn, and this increasing fire weather index. So basically the combination of antecedent precipitation, temperature, and then the strength of the winds and the relative humidity, that combination has been increasing in the autumn season statewide. And again, just simple, really simplistically, no fancy statistics, just, if we have, both temperature and precipitation contributing, and the winds contributing to the wildfire weather conditions, even without changes in the winds, just having warming in the autumn as well as drying in the autumn means that it's much more likely that when we get these strong winds, that the offshore winds in particular, strong dry winds, it's much more likely that they are coinciding with hot, dry conditions and flammable fuels. So no fancy statistics, just flipping coins here. So the first thing we do is we ask, what is the effect of these extreme wildfire weather conditions when there's very high value of the fire weather index in this case. And during the autumn, the days that have the most extreme wildfire weather index values produce much larger area burn, right? So on average, about double the area burn for the autumn season. And as you may have expected from those maps, statewide, the frequency of the most extreme wildfire weather days is increasing in the autumn, the frequency is more than doubled over the last 4 decades. So we're not saying anything about trends in area burn here or the human component of fires, but in terms of the ingredients for high wildfire weather risk, this combination of temperature, precipitation, winds and humidity is increasing very significantly. Okay, so you are probably asking this question at this point, but there's got to be a way to do this more rigorously than just counting things. So you are right. And this is a key question. It's a key question not just for drought or wildfire risk. It's a key question for many different systems, and particularly in a globalized world. Right, and we're seeing lots of examples of that. We're having multiple extreme events in multiple locations is really testing our wide variety of baseline systems that have been designed and built around an assumption of an old climate. So Amir has been a real pioneer in the more sophisticated ways to do this. So I'll note back in 2014, conference here at Irvine. So we basically used that approach, the Copula approach, to try to improve on what I just shown you. And in this case, we're interested in breadbasket regions around the world, and in particular, Just like I've been going through with this counting, right? So hot, dry conditions, low precipitation, high temperature, have the odds of low precipitation and high temperature changed in combination in different regions around the world. So if we look globally, the answer is yes. The odds of warm years have gone up globally. The odds of dry years have not changed significantly globally, but the joint probability has changed both substantially and significantly. See that both on the right, see that both in the top in the historical observations, as well as on the bottom when we compare the historical climate model simulations with human forcing and the natural ones without human forcing. So we see that globally. What about different regions? So there's a lot on this map on this slide. I'm not expecting you to take it all in. I'll just point out if we look at China and India, for example. So up on the map, what you're seeing is all the regions that we focused on here. And then on the bottom, for each pair of regions, we're asking in each of these time periods, just in the historical observation, what are the odds of a year that is 2 standard deviations warm and also drier than the baseline? So drier than the mean and also 2 standard deviations warm. What are the odds that both of those regions experience those conditions in the same year? And what you see is getting darker purple as you go to the right. And so the odds that regions have these extreme conditions in the same year overall is going up. And in particular, right, if we look at China and India, there it is. Okay. On this, on my right-hand screen, right. So the odds that China and India both have these extreme conditions simultaneously, they've gone from, in the mid 20th century, less than 5% to, in the recent period, more than 15%. So more than tripling the odds that these two regions, which together have 2.5 billion people, that they experience these extreme conditions simultaneously. All right, so that's a bit of a tour of the last several years on the hazards, right? And using this approach, general framework, and we've had, we've asked this question for lots of different events around the world. We asked it for the global scale, but we've also started to ask whether we can extend this beyond the hazard to quantify how much the climate change that's already happened is impacting us. So I'm going to show you a couple of examples of that work. So the next 2 papers I'm going to feature are from Francis Davenport's PhD dissertation. So Francis finished defended her PhD last winter, and was starting a faculty position at Colorado State in the spring. So the first question Francis asked was, how much have historical changes in precipitation in the US contributed to the cost of flooding? Right? The financial costs that we are incurring here and now from flooding. So what Francis did was to use a econometric approach, so panel regression with fixed effects. And first she analyzed the historical observations, so the historical precipitation and historical flood damages, going back 3 decades or so. And what she finds is a very robust relationship between state level monthly precipitation and state level monthly flood damages. And lots of different functional forms, and you see the same basic relationship, which is a log linear relationship, right? So there's an exponential increase in the cost of flooding as precipitation increases. And the bin regression suggests some attenuation of that at really, really strong precipitation, which makes sense given that at some point there's already been a lot of damage. But essentially, we see this exponential relationship with as precipitation gets more extreme. And then, there's a lot of analysis in the paper, but the end goal was to ask if we use this empirical relationship, and then getting back to our cartoon here, right? If we just the result I'll show you, just using the observations, if we just say how much has the precipitation changed, and what's the difference in each flood event between what really happened and the counterfactual without precipitation. So what Francis finds is that about a third of the financial costs of flooding in the US over the last 3 decades have been contributed by changes in precipitation. And it's mostly intensification of the wettest events. So the wettest events contribute the vast majority of flood damages overall. And the wettest events show the largest magnitude increase in intensity historically, and they show the clearest fingerprint of anthropogenic forcing, the clearest difference in between climate model simulations with human forcing and without human forcing. So there's a lot of money, right? And this is billions of dollars. We've repeated this with the US crop insurance program and the same analysis with the US crop insurance program, and it's similar magnitude, about 20% of insured crop losses over the last 3 decades contributed by county level warming. So we have no intention of going through every cost and adding it all up. But the point here is that not only can we extend this framework of impacts, but when we do that, we find that, in fact, the global warming that's already happening is costing us quite a bit here and now. That's not just okay. So not just costing us in the US, but also around the world. To show you a bit. Okay, so I emphasized my personal progress from counting and simple correlation to Francis, fixed effects, causal inference, and machine learning. So, all right. So what Francis next did was to go on and ask what are the causes of these intensifying extreme precipitation events that are responsible for the majority of flooding costs. And Midwest flooding is really expensive. It's not there's a lot of variability from year to year, but it's very expensive. A large fraction of the $1 billion extreme events in the US are flood events, and a large fraction of those are in the Midwest. And what we see here, if we look over this Midwest region, it's in the upper left. You can see the disaster costs on the upper right. And if we look at the bottom row, what we see is that the frequency of extreme precipitation days has been increasing in the Midwest, particularly over the last 2 decades. And we see that not just region-wide, but you can see that in the station data in the bottom 2 panels. So the question here is what's the cause of increasing frequency of extreme precipitation days, and how much of this is just the thermodynamic effects of a warmer atmosphere producing higher intensity precipitation when storms happen, and how much is due to changes in the frequency of the atmospheric pressure patterns that produce those extreme conditions. So Francis used a neural network to try to answer this question. So the configuration of the neural network is up on the top, and what Francis identified is these EPCPs, and that's just because GRL has a really short length limit, so we had to reduce extreme precipitation circulation pattern to fewer words. So EPCP is just the pressure patterns that produce these extreme precipitation days. And as we get to more and more extreme events in terms of precipitation intensity, the network is very, very accurate at identifying these precipitation patterns. So 100% of the events above 12 millimeters per day are classified. The network is able to, the network is classified as these extreme precipitation patterns. So what we've done is, now back to counting, because I don't want to give up on counting yet. So just going to go back through history and count how many days that the network identifies in each year that have this combination of pressure conditions. So on the left is the result of that counting. So it turns out you can program a computer to do this. You don't have to go through each day on your screen now. You can program to count. So that's been helpful. So on the upper left is the days per year, right, that have these pressure conditions, these extreme precipitation circulation patterns. And you can see those are the statistically significant increases in the very recent period. We're not as, the reviewers were a little bit more excited about the statistical significance of the frequency than we were. We do not identify this as an increase in pattern frequency. On the right, however, you see a very clear increase, statistically significant in the precipitation intensity when these patterns occur. And so when the atmospheric conditions come together to produce storms over the Midwest, they are, in recent years, producing more intense precipitation than they used to. And I'll show you that another way here. So if we look at the tail of those wettest years, what you're seeing on the right is just the percent change in the frequency during the recent period relative to the earlier period. And you see very large percentage increases in the precipitation intensity on those the days with those pressure patterns. And we see a little bit of increase on the other days, but not nearly as much. So the last thing we wanted to do was to try to understand why it is that these days are producing more intense precipitation. And to do that, we looked at the moisture transport on the days that have the extreme precipitation patterns, and moisture transport on the days that do not. And what you see is on the top row, the upper left is just the climatology, right? The mean moisture flux on these days over the period. And then on the right is the recent period minus the early period. So when these extreme precipitation patterns occur, they are associated with those patterns is a substantial increase in moisture flux into the region, which you see on the upper right. And much like the precipitation intensity, there's a little bit of that on the other days, but not nearly as much as on those extreme patterns. All right, I have a whole other section here that it would be better for me not to tell you about at this point, given the time. So I'll just say real quick that we've also extended this globally, and this work with Marshall Burke, just asking, given the global warming that's already happened, what have been the effects on countries around the world, and in particular on the inequality between countries around the world in terms of their per capita GDP. And this is just the same kind of econometric analysis that I already showed you, but in this case for economic growth. This is work that Marshall pioneered back in 2015 during his dissertation, and has been replicated many, many times. So the short version here is that if we take Marshall's regression between country level temperature variability and annual economic growth, and we combine that with the effect of global warming on country level temperature as simulated by the Seaman models, then we can basically calculate like how much has each country moved on this regression curve. And essentially what this regression curve tells you is that most of the largest economies in the world are right at the global optimum temperature, that makes sense. But this is not a cross-sectional regression, right? This is panel regression, so countries are being compared against themselves through time. It's a very robust result. And essentially, countries that are cooler than the optimum tend to grow a little bit faster in warm years. Countries that are warmer than the optimum tend to grow a little bit slower during warm years. So the difference in growth rate is pretty small, as you can see from the upper right here. But as with other compound interest problems, right, small differences in annual growth rate compounded over many years result in large differences in the level. So in our calculation is that Norway has warmed up a little bit, right, has moved from way down the curve up to not as far down the curve. Very small impact at an annual level, but compounded over decades. Norway is about a third, per capita GDP is about a third higher than it would have been without global warming. India, which has gone also warm, but gone down the curve, past the optimum, down the curve, is about 31%. Per capita GDP is about 31% lower today than it would have been without global warming. The global version of that is about what you would expect from the current mean temperatures. The warm countries we have very high confidence that the warm countries have been harmed, that their economic growth has been dragged down. You see that in the bottom panel. And we have some confidence that some of the cooler countries have been helped by long-term warming. And what that means is that the difference between the richest countries in the world and the poorest countries in the world, and population weighted, the wealthiest populations and the poorest populations, that difference is bigger now than it would have been if global warming hadn't happened. We're not arguing that global warming caused economic inequality, right? That was not caused by global warming, but it is larger today than it would have been if global warming hadn't happened. All right, I will spare you rest and leave the summary up. So thank you.
Yeah, I think we still have a few minutes for questions. If anybody has questions for them.
Yep.
Your thoughts on removing the low frequency multi-decadal signals?
Yeah, I think that's important, and I have never done it.
Because the changes that you show in India are parts some people are finding out from I guess paleo data and also cane data that we've had centimeter scales. So if you look at things from 1950, it might provide a slightly colored view.
Yeah, so I think the less good answer is, again, we do both. We try to calculate the counterfactual without climate models, right? And then we also use climate models to quantify the sensitivity. So in this economic analysis that I showed you, the difference between India's temperature today and its counterfactual temperature is calculated by the CMIP climate models. And so we have multiple climate models run with human forcing and without human forcing. And then for each model, we take the delta, and we take the difference simulated by each model, and then we have an ensemble of climate responses. And that uncertainty, that rhythm that I showed, that's the uncertainty across the climate model. So it's implicit in the climate model analysis. That is implicit.
I understand that, but I guess what I was trying to say was, at least in the tropics, because of the poor representation of moist convection, these models just don't get the circulation features right.
Absolutely.
So I guess at least within India, I can tell you that these CMIP6 type of sort of diagnosis forecasts tend to be looked at with a little bit of we have our own colored views about that.
Yeah.
Simply because you don't get the long-term circulation right.
Yeah, absolutely. So if the climate models are wrong, or any one of them is wrong, That's absolutely an important caveat. And India, correct me if I'm wrong, India is warmer now than it was 50 years ago. And so the regression, that's accounted for in the regression. Yeah.
Maybe I'm just gonna go back and we talked about this today, like, the travel model, the original world, but then there's some kind, and maybe for temperature, they're doing a better job for our processes. But I'm just following up on this question, it's like, if you have like a couple of models, they, for whatever reason, they have like some flaws, especially in some specific area. India is one of the tricky areas because you have the high mountain Asia there, like of the edges, and it's hard to, that's gonna buy, and I'm not saying, that's very good analysis. I think it would be nice to have more observation, more evaluation, and just figure out a way to select among this. Not saying they exist.
Yeah, absolutely. So, I mean, so there's high resolution models, there's throwing models out, there's not using any models at all. Right? So, I think, I think the challenge of trying to answer these questions without climate models is that we have a very short observational record relative to the magnitude of the events that we're encountering.
So much changes that, it's gonna get better. We have more frequent, more intensity for the year constant.
Well, certainly, yeah, I mean, the observational, the satellite record is double what it was when I did my PhD.
No, but I'm also thinking the frequency and those that, they're likely to happen more. So you're gonna have more samples, more like extreme.
Yeah.
So you just.
I'm sure the world will think
The
this.
good and the bad.
Jim.
It's really interesting to see the advances in the attribution. I guess my question is like, I think today, even in the New York Times, like Pakistan, there's huge floods in India, Pakistan. So the attribution is getting a lot better. How close are we now to like legal action following from this attribution being applied to compensation or?
Yeah, so if we weren't being recorded, I would tell you I get contacted by lawyers, right, asking how is this, and this is not just private. I mean, this is, I've never said yes to any. I'm not an expert witness, but there was in one of the lawsuits that's active, one of the judges actually convened a tutorial basically. So that's at least one judge that's already asked in the context of an ongoing lawsuit to please explain how this extreme event attribution is done. And it's interesting because actually I mentioned the Stoddard paper. There was the first paper to try it, but there was at least one paper before that by Miles Allen, co-author of the Stoddard paper, that basically said the reason we should do extreme event attribution, even though no one's done it yet, the reason we should do it is legal liability. And I think also in terms of loss and damage in the UN framework, that's another area where I think we're likely to see real financial application. Yeah.
No, I mean, what's fascinating is this: economists can come up with a model for anything and convention that works. But historically, temperature's been going one way, GDP's been going consistently different ways and patterns. But they may not have been related at all, but clearly they're long-term trends and economists can put causality in. And so, I mean, how much do you believe this issue of coming up with an economic model that says temperature is related to GDP when they've been correlated, for a long time? It's maybe unrelated.
Yeah, so this is not the cross section, and the panel regression basically compares one unit against itself through time, and fixed effects control for unit level trends as well as shocks that are common across the units. So I'm not arguing that the method is perfect, but the method is designed to do exactly what you're concerned about. I mean, to confront exactly what you're concerned about. Yeah.
I'm just curious about your thoughts, this is really interesting, about like is it possible to do attribution in places that don't have high density of weather stations and long weather station records?
Definitely possible to do it, and.
Is it possible to do it like in a robust way?
Yeah, no, I think the robust way is the key point. I mean, I think that, so the thing about attribution now is it's possible to do it anywhere. We have gridded data sets and global climate models. So it's possible to produce the numbers for anything that we have either of those, and in very, very quickly, the so-called rapid attribution. I have not personally engaged with that because of what I mentioned earlier, right? That we take a lot of time to try to actually figure out what the event is and what caused the event. Where I've dove or waded into that is actually what some people call pre-computed attribution. So, everywhere, there's a record hot event everywhere. So we can actually ask if we run this attribution analysis on that value, right? So what are the odds now of breaking that record, and what would the odds if we go through this whole thing? We can do this all in advance. So we've published maps for everywhere, every area of the world where we have the grid observations of what our calculation would be if the record's broken. So we've gone on record saying, here's what you would get in advance. Again, not knowing anything about the event, just if the threshold was crossed. And then I actually went back. So we published that in the 2017 paper, but because of the way the CNET 5 protocols worked, the historical period ended in 2005. So I went back, this was published in 2020, I got worried about this, and I said, is there a way that we can test whether or not our numbers are right? Again, a scientific sort of philosophy of science, really understand it. As I was taught in college, to be able to make a prediction and test it. So the fact that our history ended in 2005 became an advantage, because then there was more than a decade of reality that had happened since our historical period ended. So I went back and actually asked, given what we published, how many record-setting events should we have in each area of the world based on what we published? And it turned out what we published in 2017 overall dramatically underpredicted the number of record-setting events that actually happened. And I got really worried. So I was digging in that. And really what it ends up being is the standard calculation of return intervals really underpredicts the probabilities of if some location is has a non-stationary climate. It turns out a lot of areas will have a non-stationary climate. So I think NEVA is the way to go. Is the short answer.
I was gonna read the question based on the chat.
Oh, great.
So the question is like, has some of this study on socioeconomic impact of climate extreme been integrated in the decision-making process? For example, guiding mitigation strategies. So I guess what is the connection between what we are finding as scientists and how is this used and being used? So where are we standing? I don't know.
Yeah. So for me, not any concrete way. Like I haven't produced a solution personally. Like I say, I get asked a lot, right? So I've been asked by lawyers how to explain how it works. I've been asked by the state of California. It's been always been asked by Congress. So I show up and answer the questions, but so the one time I tried, I will say, so I wrote a proposal to try to make this like open source and any decision maker can calculate the change in return intervals, et cetera. And so I got to the point of like getting to where they brought in decision makers to evaluate the proposal and do a talk to me and whatnot. And the decision maker said, this is way too complicated, no one's gonna use this, forget it. That's the end of the story.
All right, let's thank you. Just one more time.